This is day 5A, folks, and why it's called 5A. Some of you heard already, but the rest of you will hear it shortly. But that's the handout you should have in front of you. And table of contents is chock full of interesting things. We're going to go through complex survey data analysis, two-level regression, both linear and logistic, path analysis, factor analysis, and towards the afternoon we're going to get into a multivariate approach to multi-level modeling, multi-level growth modeling, and perhaps even multi-level discrete time survival analysis. Mplus background, you can read it for yourselves, but it's an effort to come up with a program that you can use for all kinds of purposes. It's a program you can grow into. Actually, many installations across, or universities across the U.S. are starting to use the program already in the regression classes. And I can imagine working through the different chapters of the user's guide from the simple to the more complex models, staying in this framework. And that's the way we would like to see it. People shouldn't have to switch software when they change from, say, a factor analysis to a growth analysis to a latent class analysis to multi-level analysis. So let's just quickly say what Mplus is. It's several programs in one. Structural equation modeling is done in this program, and that's content of so-called day one that precedes this course. And that also covers item response theory analysis, which we'll touch on in a two-level form today. Item response theory simply means that you have a continuous latent variable, factor, and categorical outcomes. That's all it means. Latent class analysis we're going to touch on in this course, and latent transition analysis is another. Latent class analysis in a longitudinal setting. Survival analysis, Mplus does that quite generally for both discrete and continuous time survival. Not only does it do it like a Cox regression analysis, but it does it fully integrated into the general framework of Mplus with all its latent variables of different kinds. And the multi-level analysis that we're touching on today is multi-level in the sense that we talk about today, namely cross-sectional data, such as students within schools, and also in the growth modeling version that we talked about yesterday, where time points are nested within individuals. So longitudinal analysis, growth modeling with random effect. And Mplus is also a very strong complex survey data analysis program. So if you have national survey data with weights, clustering, and stratification, Mplus could handle that quite well. And on top of that, it's a very good Monte Carlo simulation feature, so that all of the models of Mplus can be used to generate data, artificial data, that you can then study the qualities of estimation with the help of, and also power studies. All of this fully integrated in the general latent variable framework. So slide 4 shows that framework, excuse me, with the boxes for observed variables and circles for latent variables. And what we're going to focus on today is different levels of data, different hierarchies of data. So this could represent relationships between variables that vary within the cluster, for instance, students varying within the school, and between clusters, variation between clusters, such as variation across schools, which will be the focus of today. And as we showed yesterday, we were talking about day 2 yesterday, which is a continuous latent variable setting for longitudinal data. We're going to skip day 3 and day 4, which we covered in March earlier this year, and go straight into day 5, which has both continuous latent variables and categorical latent variables, both cross-sectional models and longitudinal models. And we're going to try to cover all of these models, all of these 4 cells, and that's why day 5 had to be split into 5A and 5B. Particularly since there have been some recent developments in this area that we have done, and also because we wanted to take a little bit of time tomorrow to go through what's forthcoming in Mplus version 5 this fall. Some nice features for multi-level modeling is what we're going to talk about. And there are several other features that are being put together right now. So let's start with the complex survey data.
And let's make a couple of announcements also first. One announcement that they've asked us to make is that no food or drink in this room is allowed in this room. So please don't bring your coffee with you or anything to eat. And the people that were here yesterday will know, we break the day into 4 segments of about 1.5 hours each. And we ask people to write their questions down if they have any as we're presenting. And if they haven't been answered by the end, then we always have a long question and answer session at the end of each segment to allow you to ask your questions. So that's just an administrative detail that I wanted to share with you now that more people are here.
Yeah.
Okay.
Yeah, we're going to have a fuller house today than yesterday, but not everybody has found their way here, I think. But they will come. All right. And the person who spoke is actually then Linda Mutén. And I'm Bengt. So let's start with a basic observation about these kinds of data that we're going to talk about, multi-level data. Data that have been obtained by cluster sampling or unequal probability sampling leading to the need to use sampling weights. And as we will talk about also, data that have been obtained by stratification. The question is, how should you deal with those kinds of data in the correct way to not get biased parameter estimates or biased standard errors? That's what we're going to talk about. And how are we going to be able to analyze the data in the most informative way? And we're going to make some distinctions between different kinds of approaches to analyze such data. We're going to talk about the sampling perspective, and we're going to talk about the multi-level perspective. So in terms of the sampling perspective, on slide 8, by sampling perspective we mean the perspective that's presented in sampling theory books, statistical books like Cochrane's classic book. So the perspective of sampling statisticians who are concerned with getting the right standard errors for parameter estimates, such as the mean for the nation's various recordings of health statuses or income statuses. We're going to refer to that quite often as aggregated modeling, and that's a term versus the disaggregated modeling in the multi-level perspective. These are terms that were coined by the British sampling statistician Skinner. And in your reference section at the end of your handout for 5A, you have a reference to a book by Skinner, Holt, and Smith, Complex Survey Data Analysis or something like that. I think it was 1989, a Wiley book, which is an edited book which is great for complex survey data analysis. And there's a new version of that from, I think, 1993, maybe later, follow-up, which also has Skinner as one of the editors. And I'm going to tell you a little bit more about what aggregated modeling is in a second. One particular piece of software, Sudan from RTI in North Carolina, is noteworthy because it specializes in doing aggregated modeling correctly. So, for instance, estimating means, doing linear regression, logistic regression, estimating proportions, and attaching the correct standard errors to those quantities under various kinds of sampling schemes, with or without a replacement, etc. So that's a very good program that has some good methods, but mainly, or only, I would say, focusing on univariate response models, so not multivariate models that we're going to talk about, and certainly not latent variable models that we're going to talk about. And we actually have a project, an SBIR, Small Business Innovation Research Project, through NIAAA, the Alcohol Institute, for continuing, phase 2 now, continuing work on developing more technologies for handling complex survey data. And some of that writing is on our website. Some of those analyses are obtained by the Mplus keyword option type equals complex, which allows you to specify how the clustering took place, what the sampling weights are, and what the stratification variable is. And here's a particularly relevant paper by our statistician in the Mplus team, Tijermer Asparojo, who takes the lead on that work. It's on our website. It's a paper in the Structural Equation Modeling Journal, an overview paper of techniques in that area. So what is characteristic of this approach is that you, if you do a regression analysis, you're going to estimate the same parameters as you would in a regular regression, but all that's new is that you get different standard errors. And in contrast to that, the multi-level disaggregated situation actually adds new parameters. So not only do you have your usual alpha and beta, but you have more parameters. You have parameters for level 1 and for level 2. So you have a higher level of ambition up here in the disaggregated modeling. Not only do you correct standard errors, but you actually estimate different parameters. You estimate more parameters, maybe twice as many parameters. So it's a richer approach. So here you're just trying to avoid mistakes. But up there, you're trying to learn more out of your data. That's essentially how I see it. And in Mplus, you describe this by type equals two-level modeling. Two-level modeling to estimate the model at both levels, primarily taking into account the clustering. The clustering is modeled as a two-level model. And for those, we'll see several instances of this. If you ignore clustering, you will ignore a certain amount of non-independence of observations. So when you have clustered data, you have non-independent observations. And the multi-level perspective is a way to, multi-level model is a way to model that non-independence of observations, which is then totally in line with, totally analogous with what we talked about yesterday in the growth modeling situation, where we have correlated observations across time for the same individual. And there, too, do we take that non-independence into account by modeling, namely by having random effects, growth factors, that influence the outcome at all time points, and therefore capture the correlated nature of the data. So if you have a complication in your data collection like correlated observations, if you take that into account in your model, you're okay. And in the two-level case, you can still allow for sampling weights and stratification. And I think it's good to do that, take into account all of these things, clustering, sampling weights, and stratification, because the sampling statisticians have worked really hard on carrying out these sampling schemes. For instance, using stratification is designed to lower your standard errors, to shorten your confidence intervals. That's a good thing. So for instance, in areas like structural equation modeling, for decades, people totally ignored the fact that the data was not simple random samples. And therefore, they shortchanged themselves because they got larger standard errors than they had to by ignoring stratification. So ignoring stratification, your standard errors are too large, unnecessarily large. Ignoring clustering, as we will see, is the opposite. Ignoring clustering, your standard errors are too small, which is going to mean that you're going to say that your effects are significant more often than they are. And sampling weights, that is affecting the parameter estimates as well. because it's the fact that you have sampling rates is acknowledging that different parts of your sample may have different parameter values. It's almost like a multiple group analysis, but we'll get to that more. Now, a version of the multi-level perspective is the multivariate modeling, and that is exactly what we talked about yesterday, all day long yesterday. So yesterday we had a multi-level situation, a two-level situation. So we had the highest level was individual. That was the cluster. And within individual, we have repeated measures. Those are the cluster members, so to speak. And what we did was to take the multivariate single-level approach to that kind of data. We said that you could do a univariate two-level approach, but we actually took a multivariate approach to the multi-level data yesterday, all day long. And we could yesterday have worked with clustered samples, sampling weights, and stratification as well. A relatively new feature in Mplus is that we can have a combined sampling and multi-level perspective, which makes it possible to handle more levels of hierarchies. So we can talk about type equals complex two-level. So for instance, if you have students within classrooms within schools, you can have a two-level model for students within classrooms and then let the complex feature refer to the school level. And the reason one might want to do that is that usually on the lower levels is where most of the action is. So if you talk about variance for, say, an achievement variable, it's highest on the individual level, second highest classroom level, third highest school level. So most of the action, most of the variation is on the lowest two levels, student and classroom. And you can do a two-level modeling of that and just correct for the non-independence that you incur within schools by having school as the cluster level in the complex approach. Same thing if you have individuals within households within geographical segments. So then you have a two-level model for individuals within households, and then you correct standard errors for the non-independence within within geographical segments. So that's quite useful to extend it up one level, because right now, as it is in cross-sectional situations, Mplus can only handle two levels. If one of the levels is longitudinal, Mplus handles then three levels very easily, because one of the levels gets reduced by the multivariate approach. So this is a way to extend up one level. You don't model that highest level, but you at least get the right standard errors for it. So we're going to talk about multi-level modeling in several different settings. Very often I find that when people think about multi-level modeling, all they think about is multi-level regression. Or possibly they talk about growth modeling. So it's growth modeling or regression. And I wonder why. If you think that multi-level modeling, multi-level issues are important, they apply to everything that you might want to do. Path analysis with mediational ideas, multi-level factor analysis will be relevant. Structural equation modeling, multi-level setting is important. Growth modeling, well, that is part of the tradition. But what about latent class analysis, transition analysis? Growth mixture modeling. All of these kinds of techniques should add a multi-level feature to them. And that's what we want to convey today and tomorrow. Now, just looking at some formulas here, quickly. We want to have some basic formulas clear in our minds. And the first concept that we want to have clear is the so-called intraclass correlation, which is a measure of the degree of non-independence of observations. And we can start then by reminding ourselves of the standard, simple, random effects Anova. You know, there's fixed effects Anova, which we studied first, treatment control, for instance, but then there's also the random effects Anova. And here's the random effect Anova for Y, outcome Y, where the clusters are today denoted by J, and the individuals within cluster are I. So you have a mean here, nu, that's a mean, NU, a Greek letter, nu, and a cluster variable, eta sub j, and a within cluster variable, epsilon ij. So the subscripts give away what they are. So eta j is the cluster level variable. It's both nu and epsilon are latent variables. They're not observed. Random effects Anova is a latent variable model. You never thought about them, right? But it is. We try to incorporate everything as latent variable modeling. Very imperialistic approach. So you have then j clusters, for instance, schools. And within each school, you have n sub j students. The number of students within schools could vary. And what you're interested in is the variance of y, which is equal to the variance of eta plus the variance of epsilon. They are uncorrelated, these two, by this model. So the total variance is the variance of the eta plus variance of epsilon. And actually, yesterday, these two lines may be a little bit confusing, but yesterday we had that situation. But it was time point that functioned as I, namely cluster member, and individual that functioned as j, namely the cluster. So individual, or ID, was the cluster variable, right? And within the person was the time points. So this is a repeated measure model as well, if you think about time points as being the cluster member index. And actually, if you look at it carefully, then what, in terms of repeated or growth modeling terms, this is a random intercept model. We only have one random effect here, which is not connected with time scores, so therefore it must be the random intercept. But you can forget about that if you hadn't woken up enough to follow that reasoning. Now back to the story here of students within schools. So now you may consider covariance and variance. I equals k and I equals L. And if you use this formula 44, covariance is between two members in the same cluster, cluster J. Two members of cluster J, the covariance between them is actually the variance of eta, the variance of this eta variable. And the total variance, like we said, is the variance of eta plus the variance of epsilon. And you may want to scribble here that the variance of eta, the variance for the cluster, we're going to call the between variance. The between variance. So you can write like sigma squared between here for variance of eta. And variance of epsilon is the within variance. So the total variance is equal to the between plus the within. And from that, then you define the intraclass correlation as the between variance divided by the total variance. The between variance divided by the total variance. It is a correlation because it has the usual correlation formula, covariance divided by the product of the standard deviations. So there's the intraclass correlation. And you can see then that the interclass correlation is high when the proportion of the between variance is high relative to the total variance. So for you to have an intraclass correlation different from 0, you have to have variation across the clusters, across the schools. You have to have between variance. Otherwise, the numerator would be 0 and the interclass correlation would be 0. So if you have cluster samples, but it turns out that there's no variation across the clusters, but only within clusters, well, then you don't have to worry about using these techniques today. So that's the basis for interclass correlations. And we have an example of this, Endless Y National Longitudinal Study of Youth, that we looked at the cohort picture for yesterday. And we have their households. And we have households with single members, with 2 members, with 3, 4, 5, 6 members. Total number of households, 8,700. And 12,000 respondents. Average number of respondents per household, 1.4. And you can ask yourself, what's the intraclass correlation for household members within households? And here, intraclass correlation sizes depend on very many different things. First of all, it depends on which variable are you looking at. Well, we're looking at heavy drinking frequency here. Second, which clustering context are you looking at? Well, in this case, you're looking at individuals within the household. So they interviewed many individuals within the household, and particularly young people in the household. And you see then that the interclass correlation here varies from 0.19 to 0.06 as the years go on in this longitudinal study. And probably the interclass correlation goes down over age because of household members. The children get older and move out of the household and become less alike. But in any case here, you have about interclass correlation about 0.2, and you then want to ask yourself, well, is that serious or not? And in what regard might it be serious? So that's where the def comes in. Def being the design effect. So far now, we're reasoning from the sampling perspective. We have not gone to the multi-level perspective yet. So consider, for instance, the cluster sampling with a simple case of equal cluster sizes and considering the sampling variance of the mean. And when I say sampling variance, sample statisticians talk about estimating the variance of something. When they say estimating the variance, they mean the standard error squared. So when they talk about variance estimation a lot. In more common terms, they're talking about the standard error squared. So we have a mean estimate like x bar, and we want to have the standard error for it. And that standard error is the sampling variance square rooted. So we consider now this then, according to statistical text, has a certain variance on the cluster sampling. VC then is the square of the standard error once again on the cluster sampling. And since we did cluster sampling, that is the correct variance. But we also can ignore that there was cluster sampling and just act as if we have simple random sampling, which I said structural equation modelers did for decades and live happily through that, but shouldn't. So that variance actually under simple random sampling is smaller than the cluster variance. It's smaller, incorrectly smaller. And that's what I said. If you ignore clustering, standard errors are too small. It is smaller. Now you may ask, well, why do we do cluster sampling if our standard errors get bigger? Then we get too big. Then we get such big confidence intervals. Well, it's so much more convenient, practical to do cluster sampling. You know, if you're going to interview a lot of people, it's better to first locate their homes and then interview a lot of people in that home. It's much more practical. So that variance is bigger, but it's much more convenient to do cluster sampling. Now, so there is where def comes in. It actually looks at the ratio between cluster sampling and simple random sampling, which is then greater than 1 because the numerator is greater than the denominator. And for this special case, the formula is 1 plus s minus 1 times rho, where s is the common cluster size and rho is the intraclass correlation. And interclass correlations are typically fairly small. You know, 0.1 is actually a fairly high correlation in that setting. But it is really the product of the size and the correlation that influences def. So in this case over here, you can figure out then 0.19 times average number of respondents per household, 1.4 minus 1, it won't get that high of a def because the number of people per household is not very big. But we're going to take a look at math achievement in U.S. schools where the interclass correlation is like 0.1, and if you may have 60 people within schools, and therefore the interclass correlation, the def will be higher. And generally speaking, you don't want to ignore defs that are 2, something like 2 or higher could be a rule of thumb. You don't want to ignore them because if they're that large, you may make a sizable mistake in terms of your standard errors. And with that, I think Linda takes over.
Okay. So to give you an idea of, oh, you have the same thing on both. Okay. To give you an idea of how this actually might affect your data, we generated some data. Actually, I guess Bank generated some data. So and that using the Mplus Monte Carlo facility. So we generated with data that had 200 clusters of size 10 with an interclass correlation of 0.2. And we generated using type equals 2 level. And we're going to analyze it in 3 ways. 1, multi-level, type equals 2 level. 1, type equals complex, where we're just going to be adjusting standard errors, not actually modeling the clustering. And then 1 as a regular analysis, ignoring the clustering. And the def for the data that we generated was 2.8. And as Bengt mentioned, we don't want to ignore anything great with a def greater than 2. But in cases that we'll talk about later, even if you don't have a large design effect, you might still choose to model using multi-level modeling just because you're interested in the parameters on both the between and the within levels. So it isn't always a reason. You don't always need to have a def greater than 2 to use 2-level modeling or to make adjustments. But if you have something greater than 2, you don't want to ignore that. As Bank said, your standard errors will be too small. So the Mplus input on this screen, your right screen, is the input for the 2-level analysis. And that's the exact analysis that we use to generate the data. So you can see in the analysis command, we have type equals 2 level. And in the variable command, we have cluster option, where we specify what the cluster variable is. And in this case, it's called cluster. And you see that in the names option of the variable command, we have 2 variables. We're generating a y variable and a cluster variable. And the y will be used in the analysis, and the cluster will be used as the cluster variable in the analysis. So in the model command, we're simply estimating at the within level the variance of y, and the between level the variance of y. And since this is the first time we're seeing this new language, let me just discuss it a little bit. So in the model command, where you specify the model that you're going to estimate, when you have a 2-level model, you have to use the keywords % within % and % between % to give the within, or the level 1, and the between level 2 parts of the model. We didn't mention this yesterday, but when you want to refer to the variance of a variable, you just refer to the name of the variable. So when you see y semicolon, that means the variance of y. So on both levels, we're going to be estimating a variance for y. And we'll be discussing this a little bit more later, but when you don't specify that y is either a within or a between variable, then it can be modeled on both levels. That's why we're able to refer to it on both levels. So this is the analysis for 2-level, and you'll see the model results. And for those of you who weren't here yesterday, the first column is the raw coefficient. Second column, the standard error of the parameter. And the third column, the ratio of columns 1 and 2, which is a z-score. So this is what you would use for checking for significance. And the values that we show here, the variance on the within level 0.779, that's the same value that we used to generate the data. So we are going to reproduce exactly what we generated because we generated it as a 2-level model. And on the between level, we have the variance of y, 0.212, and we also have the mean of y, which is estimated as the default, which is 0.003. And you can see both of the standard errors are what we're really interested in. On the within level, 0.025 standard error for the variance of y, and on the between level, 0.028. Now, when we ignore the clustering, those variances should be smaller. So they should be estimated as smaller than they actually are. So let me leave those results there. And let's then look at the input for type equals complex. And how would we change the input? Well, in the variable command, we still name a cluster variable when we have type equals complex, because we are adjusting non-independence of observations due to clustering. However, in the analysis command, we say type equals complex, and in the model command, we don't have to say anything since we're just estimating the variances. So we don't have a between part and a within part. We don't have level 1 and level 2, because all we're interested in is correcting the standard errors for the non-independence of observations due to clustering. And what we see here is that then in the results, we don't get a within and a between part. We just get one single set of results, a mean and a variance. And you can see that the mean is the same as it was on the within, and the variance is actually the sum of these two, and the standard error is 0.036. So these are two different ways of adjusting for clustering. And then I think the third way is more comparable to complex, so I'll come over here. Right. And you do get the correct standard error here because you're making the adjustment. Now, what if we decide that, that we want to ignore the clustering? And that's what most people do, not just in SEM, but in everything. I know it came as a horrible shock to me when I was in graduate school, and I realized that SPSS and SAS and BMDP at that time, all the analyses in those programs assumed simple random sampling. And it just had never occurred to me, and I was shocked because most of the data were not simple random samples. And my little naive question was, well, how can that be? And everybody just goes, oh, push, ignore, just ignoring the simple graduate student who's trying to do things right, and everybody's going, oh, well, we've always done it this way. So this is how we always used to do it. We just ignored it. So you can see the difference in this input is I put an exclamation point in front of cluster equals cluster, and what I'm saying is we're ignoring the fact that these observations are not independent, which is what is required for analyzing them as a simple random sample. We're going to just ignore that, and we're going to analyze the data anyway. So when you do that, here are the results that you get. You get a mean, and note that the parameter estimates are not affected by the non-independence of observations. As Bengt mentioned, parameter estimates are affected if you ignore weighting, and we did not generate this data as weighted data. So the parameter estimates are the same, but the standard errors are smaller when you ignore clustering. So we have 0.036 here, 0.031 here. And in this situation, the significance is not affected, but in many situations, if your standard errors are smaller, and let's say you have several covariates, the pattern of significance of your covariance could be dramatically affected. I mean, you could have published saying that certain covariates were significant based on the fact that your standard errors were too small. Another effect that we don't see here because we have a just identified model is that your chi-square will be inflated. So if you ignore non-independence of observations, you could actually think that your model fits worse than it does fit. So both of these things have to be taken into consideration. And Bengt also mentioned that standard errors might be larger if you have stratification. So if you have data that are not a simple random sample, there can be a lot of things going on. And you might say, well, maybe it all balances out and it's okay in the long run. Well, maybe, but you can't really know, so it's best to actually model the data appropriately. And we have a lot of further readings on complex survey data. Our statistician Tiamir has done a lot of work, and there are a lot of other articles of his on the website. I'm not as familiar with these books, so maybe you want to say a word about which of the readings you consider to be most important and why?
Yeah, so here is the Skinner, Holt, and Smith book I was referring to from 1989, and here is the 2003 updated version with new contributions by several writers. So those are recommended, particularly for those of you who like a little bit more technical stuff. If you want the general book on complex survey data, that's sort of an overview book, a textbook. This one, Korn and Gravard, is pretty good. And here's a more applied paper by Laura Stapleton in the SEM journal, sort of a more applied version than Asparohov. And this is also quite useful. Here it is applied to latent fast analysis.
Okay, so now the first in Bank's list of models that we were going to look at was a two-level regression model. And so we'll spend some time on this first slide over here. And for those of you who were here yesterday, this slide should look very familiar. We looked at it about at least 10 times probably. We saw the slide yesterday for the growth model, which is very similar to this. The one difference is instead of Yij, we had Yit yesterday, and instead of j on these coefficients, we had I, and instead of beta, we had eta. So yesterday we were talking about random effects, the intercept growth factor and the slope growth factors, so eta sub 0 and eta sub 1. But today in regression analysis, we're going to be talking about beta sub 0 and beta sub 1. And they are also random effects. So in the regression of y on x here, the intercept, beta sub 0, is a random effect coefficient, not a fixed effect coefficient as in regular regression, but it will have a mean and a variance, and it will vary. It's not going to vary across individuals like the growth factors did yesterday, but it's going to vary across clusters J. And then we're going to have beta sub 1, which is the regression coefficient for the covariate x, and that's also going to vary across clusters. And then we have a residual. So, and as in yesterday, we have a level 1 equation, and then we have level 2 equations. So on level 1, we have, for example, our outcome y on the y-axis, x is a covariate. So on the x-axis, it's no longer time. It's a value of a covariate. So perhaps it's student level SES, ranging from low student level SES to high student level SES. And maybe the y-axis is math achievement. And so we're not talking about growth, but rather we're looking at the fact that in the relationship between student SES and math, the random intercept may vary in the regression of y on x for individuals, varying over j, and the slopes within clusters may also vary. So for example, in cluster 3, perhaps the intercept is lower and the slope is lower, whereas in cluster 1, the intercept is higher and the slope is higher. And because the intercept and slope are random effects, they're variables. And they're variables on the between level where, as shown in equations 2a and 2b, they can be regressed on cluster level covariates. So Wj is a cluster level covariate. And we can, as we did yesterday in explaining the growth factor variation, we'll be able to explain the variability in the random intercept and the random slope of the regression of y on x. And so another difference is x here is the variable that varies for individuals. It's not a time score, as it was in yesterday's growth model. But there are similarities that should help you understand this a little bit better. So let's look at the next slide, which explicates this a little bit. So this just gives you a little bit more information. So individual I, remember, is in cluster J. Yij is the individual level outcome variable. Xij is the individual level covariate. So the data in the analysis are going to be an outcome and a covariate measured on the individual level. And Wj is a cluster level covariate. So because beta 0 and beta 1 vary over clusters, then we're going to be explaining cluster level variability using a cluster level covariate. So here, so we're having random intercepts and random slopes. This is a repetition of the formulas over there. And then just to bring this into the context of, for those of you who are doing multi-level modeling with other programs, Mplus gives the same estimates as HLM, MLWin, although using maximum likelihood with MLWin, not the restricted maximum likelihood. You're going to see the variance of R, the residual variance for level 1 on the within level, and all the other coefficients, gamma 0, 0, 0, 1, 1, 0, 1, 1, the variance of U, or the residual variance of U sub 0, U sub 1, and their covariance will all be found on the between level. But you will get the exact same results if you analyze this in any other multi-level program using the same estimator. And we'll be centering variables where you can subtract either the grand or the group mean. That's allowed in Mplus. And as we saw yesterday, it's sometimes convenient to do that for purposes of interpretation. So that's your multi-level regression. So let's take a look at an example. Today we're looking at data called the NELS data from the National Educational Longitudinal Study. And basically, children were measured on a variety of variables in grade 8, followed up in grades 10 and 12. There were 1,035 schools and about 26 students per school. We're going to be looking at math and some background variables today. And this just came into my mind. We have 1,035 schools. That's a very healthy number of clusters. We recommend no less than 30 to 50 clusters. So if you have only 4 clusters, that's not really enough to actually do type equals complex or type equals 2 level. So then the way to think about it is that the number of clusters is actually your sample size on the between level. And you wouldn't think a sample size of 4 or 10 or 15 was probably enough in most situations. So between 30 to 50 is what's recommended as a minimum. And it's also recommended, and we warn you, that you have more clusters than parameters in your model. We complete the analysis for you if you don't, but we warn you that we're not sure the impact of having more parameters than clusters might have on your results. We think probably it's not a big problem, but we haven't had time to explore it. And if there's somebody looking for a dissertation topic, that might be a good one. Then we could take our warning out. So let's take a look at a path diagram now for a math achievement regression 2-level. So I'm showing on the left here within part of the model, level 1 part, between the level 2 part of the model. And what do all these new filled in circles mean? Well, we're regressing. The arrows pointing to a variable. The variable that they're pointing to is the dependent variable. So M92 is the dependent variable in the regression of math on female, which is a dichotomous covariate where 1 is female, and also regressed on student SES. So this is a simple regression of math on 2 covariates, female and student SES. And the circle on the Math 92 box means that a random intercept is going to be estimated. The circles on the arrow between female and Math 92, the circle labeled S1, means that we're going to estimate a random slope. And the same thing, the S2 on the arrow pointing from student SES to Math 92 means we're going to be estimating a random slope for student SES. So we're going to be estimating one random intercept and two random slopes. Now, if this were a fixed effect model, there would be no filled-in circles here. It would just be M92 on female and SES. So these represent random. And we have to recall the random intercept on the between level M92. We just give it the same name as the observed variable. But we have to give names to the random slopes, and so we're going to name the slope for female S1 and the slope for SES S2. So because they're variables, we have to be able to refer to them in their regressions when we regress them on between level covariates. So we had to come up with a convention, and we decided, and we'll see how that plays out in the language. So on the between level, what do we have? Well, random intercept M92, the random slope S1, and the random slope S2. And we're regressing them on a set of covariates per ADVA, which is the percentage of teachers who have advanced degrees, so a master's or higher. Two dummy variables, private and Catholic, which represent a three-level nominal covariate that's Catholic, private, and public. So this is private compared to public and Catholic compared to public. And then we have SES, a between-level SES variable that we're also using as a covariate. So let me talk about language now that's specific to two-level modeling. In the variable command, we have the within option, between option, cluster option, and centering option that are used with type equals 2 level. A variable that is placed on the within list, like we're doing with female and student SES, it means that that variable is measured as a student level variable, and it will be modeled only on the within level. So it's modeled only on within. Any variable that's on the between list, per ADVA, private, Catholic, mean SES, has to be measured on the between or level 2 level. So that means that basically a variable like that, everyone within the cluster will have the same value on that variable. And if you put it on the between list and you don't have the same value, we're going to complain to you. And that variable will be modeled on the between level. Now in Mplus, if you don't put a variable that's on the used variables list on either the within or the between lists, then it is going to be modeled on both levels. So you need to be sure that you understand this and that you appropriately specify these. So within will be modeled only on within, between will be modeled only on between, and a variable, an individual level variable that is not put on either of those will be, on the within rather, will be modeled on both, within and between. And another thing I wanted to mention, I think in some of the other programs, the data the within and between variables have to be in different data files, and that's not the case in Mplus. Your data is in one file. If it's a between variable, it will be the same value for each person in the cluster, but you don't have to do anything other than that. You don't have to put the data in two different files. Cluster option names the variable that contains cluster information. So in our case, that's school. So students are nested within schools. And then we have the centering option. So if you want to center your variables, you just say centering equals, and you give either grand mean or group mean as a keyword, and then in parentheses you put the names of the variables you want centered. So we'll be centering student SES per adva mean SES by the grand mean. In the analysis command, we have now the 2-level option, so type equals 2-level, and then random. And we have to include that when we're estimating random effects. You don't have to do that with the growth model because we take the multivariate approach, but in this situation, we have to specify random because we have these filled-in circles. And then we're saying missing because we want all variables or all observations included in the analysis. Now in the model command, how do we specify that these regressions are random over here? Well, in the within part of the model, we use the bar command to define S1 and S2. We don't have to define the intercept. That's going to be random automatically. So we say S1 bar, and then M92 on female. So we use the on option, which is short for regressed on, to say M92 on female, the random regression coefficient is going to be named S1, and S2 is going to be the name of the random regression coefficient M92 on student level SES. Now, if we just had this on within, we would be estimating fixed effects. So that would be a fixed effect regression. So if, for example, you found in your analysis that actually the variance of S1 was going to 0 and it was causing convergence problems, well, you would just take this away and you would estimate it as a fixed effect, because that's basically what that would be telling you, is that you didn't have any variability in that regression coefficient. So it isn't a random effect, it's a fixed effect. And we find that that happens more often than we thought it would, that regression coefficients often aren't random. And you may find in your analysis, you also don't want to put in like 7 or 8 of these at the same time, because things will just be exceedingly slow, because out of those 7 or 8, probably maybe 1 or 2 are random. The rest are variances are going to 0 and just making your computer sit there all day doing nothing. So we recommend that you use these random effects sparingly and just do them 1 or 2 at a time to see whether or not they are random and make them fixed effects if not. But we have these 2 random effects, and so what do we have on the between level? A random intercept and 2 random slopes, which we want to regress on 4 covariates. So we just use our on option, and we say M92, S1, S2 on, and then per adva private Catholic mean. In the on statement, you can have several variables on the left-hand side as a convenience feature, and we just then internally create 3 on statements, M92 on, S1 on, and S2 on. So all the covariates on the right-hand side are used with all the independent variables on the left-hand side. And now we've added M92 with S1 and S2, which we show the residual covariances in our path diagram. But we add those because with type equals, we have different defaults in Mplus for the more complex models. And these are based on what we find might make convergence more difficult in some situations. And it doesn't mean you can't have those parameters. It just means you have to ask for them specifically. So here we're wanting to look at the residual covariances between the intercept and the 2 slopes. And we use the with option to do that. So we'll be seeing that in the output. So let me just check the time. Doing well. All right. So what do we give you that's different in the output than we saw yesterday? Well, we'll note also that we have like 11,000 observations here. 902 clusters. And we show you a summary of the cluster sizes with the cluster IDs. So for example, clusters of size 1 are represented by the school variable value of 89863. So school 89863 has a size of 1. And then we have clusters of size 2, 3, 4, 5, all the way up to size 43. And the numbers to the right are just simply the variable values on the school variable that have clusters of that size. The average cluster size is 12, just a little over 12. And the estimated intraclass correlation for M92 is 0.107. We were giving all of this cluster information as the default in the output. In version 5, we're only going to be giving all the cluster information in type equals basic, and we'll only be giving this amount of information because it was making the output really, really cumbersome for people. So we'll be changing that. And then we have our tests of model fit. And now we're in a situation where there isn't a single covariance matrix that we're looking at to test against. There's one for every value of x. So we're not going to get chi-square statistics that we're used to. We're just going to be getting log likelihood and different information criteria like the AIC and the BIC. So let me put the rest of the output on the other screen. And see what we have. So as I mentioned, on the within level, the only value that we're going to estimate is the residual variance of the outcome variable, M92. And so that's on the within. And on the between level, we have the regressions of the 3 random coefficients on the 4 covariates, so S1, S2, and M92. And you'll note in the third column that none of the covariates are significant for the gender slope. Is that the gender slope? Yeah. Right, for the gender slope. So you have to kind of relate this back to the picture and remember that S1 was the regression of M92 on female. And so S1, so when we're looking at this regression, we're talking about explaining the variability in the female slope. And here we're talking about explaining the variability in the student SES slope. So S2 was the regression of M92 on student SES. And here we have all of the covariates are significant in explaining the SES slope. So as the percentage of teachers with advanced degrees increases, we have a positive significance here, then the S slope increases. And here we see that the S slope is going to be higher for public schools. And as the school SES increases, so does the slope of the student SES slope. So this is how you reason here. So you're explaining variability over clusters in the slope coefficient, in the size of the slope for these different clusters. And for M92, that's the variability in the intercept in the regression of M92 on the 2 covariates. So there's 1 intercept and 2 slopes in that regression because it's M92 equals an intercept plus the female slope plus the student SES slope. And we see here that only 1 of the covariates is significant for the intercept, and that's a positive relationship. So it's saying as the cluster SES increases, the intercept increases. Now we also have the width statements that we added. So the female slope covaried with the intercept, and the SES slope covaried with the intercept. And we see that only one of those is significant. So as math increases, then, as the intercept increases, the female slope decreases. Now so this is the mechanics of it. So let's take a minute to try to think about what this might mean. So for example, what about the finding for private schools and Catholic schools? With the negative coefficients, it's saying that public schools have higher SES slope. So the SES slope is the relationship between SES and math. And it may be that the public schools are not, so it's basically saying that schools with higher SES have a higher slope, and in the public schools versus the private and the Catholic. And so maybe the public schools don't have as much control over that aspect. Maybe they don't have as much control over the fact that schools in better neighborhoods may attract better teachers that may make their growth rate, or not their growth rate, but the slope for math and SES higher. So these things are not the most easy to interpret, but because you have to keep in mind that it's a slope, but it's also a variable. So it's a variable that takes on different slope values. So you're looking at the relationship between two variables. And so, for example, as the percentage of advanced degrees goes up, so does the slope. And that's sort of in line with what I was saying about the mean SES. So as the number of students with advanced degrees goes up, then the slope for predicting math from SES also increases. So I see a lot of blank faces. Do you want to give it a try? You don't want to? Okay. Well, okay. So we're going to be talking about these things a lot. I mean, I had to sit and practice at home, months ago when we started this, going, wait, no, it's there, but wait, it left my mind. I can't get my mind around it. Because you have to go back and you have to remember what the label means. The label is a label of a regression. And, so you have to take your time in thinking these things through. I have no substantive background in anything, basically. When you have, you have the advantage that when you're looking at your results, you know what your data mean. So you should be able to come up with some really good stories.
Well, I've been in a school of education for 25 years, so I've heard some corridor talk about.
Do you want to add?
Yeah, it's just that I think the relationship between student SES and student achievement is one that education people want to be low. They want to have that slope be low. They want to have a low prediction from SES to achievement. And a school that achieves low slope is an egalitarian school. And what Linda was saying is exactly that, namely that private schools and Catholic schools are more successful at lowering that slope than public schools are. So that's just another way of saying the same thing.
But always keep in mind, these are just illustrative examples. Okay. Whoops. I guess it did. Oh, there it goes. Okay, should I try to do these next few slides before break? Okay. So I'll start over here. To bring this also into a context for those of you who use other programs and hear other type of jargon, we often talk about cross-level influences. And for example, the between-level variable, W, influencing a within-level variable, Y. So we want to be able to talk about Y influencing W. And so let's look at a random intercept. So in this model, Yij equals, you can see beta 0 is random because it has a J on it. beta 1 is fixed because it does not have a j. So in the regression of beta 0 on a between level covariate, we can put this into this equation. And then we have y on w. So w is influencing y. So let me just say that again. So if you take the right-hand side here and place it up here to replace beta oj, then y is regressed on w. So we obtain that effect of w influencing y. So that's how this comes about. And in the Mplus language, y on x estimates beta 1, so right here. Y on w estimates beta 0 and gamma 1. So that's the logic of how that comes about. So y on x, once again, that estimates beta 1, which is up in this first equation. And y on w estimates both beta 0 and gamma 0, 1. And if you replace beta 0j with the right-hand side, then that's part of that equation. Now, if you want to instead get what is referred to in the literature, I guess, as cross-level interaction, or a between-level variable, level 2 variable moderating. So moderating being an interaction, a within-level variable relationship. Then we have a situation where we look at a random slope. So here's the same equation as we saw, except now we have a random slope and a fixed intercept. So beta 1j equals, and then we have it regressed on a between-level covariate. If we put this up here, then x and w are multiplied together. So that's where the interaction comes about. So that's where we get this moderating, this cross-level interaction. It's the fact that when you replace beta 1j up here in the first equation, then x and w are multiplied together. They become a product being an interaction being a moderating effect. And how does that happen in Mplus? Well, we have to use the bar to define the random regression coefficient. So beta 1 bar y on x, and then in the between, beta 1 on w. And then we get gamma 1, 1 from in that way. Okay, so perhaps it's 9:45. Should we take questions, or
Yeah.
let me just look ahead?
Let's do that.
Oh yeah, or maybe that's the last thing. Are we doing that one? Oh yeah. No, let me do this quickly, and then we'll be done with this section. This is actually a slide we saw yesterday. The top part, basically, it describes the fact that we can't get chi-square and related statistics because we don't have a single covariance matrix when we're in type equals random. We have a different covariance matrix for each value of x. And we talked about that earlier. And I think I talked about this point earlier, too. If you have a very small variance for one of these random slopes, it can make things converge very, very slowly. So take them one or two at a time. And if they're not random, make them fixed. And then the fact that we can have predictors that are unique to Mplus. Not only can we have observed covariates, like we've been seeing y on x or per adva observed variables, but our covariates can be dependent variables, creating a mediation situation, or even continuous latent variables can be covariates in these models.
Well, I have to say, I just love a woman who talks formulas.
Okay, I think we should take questions.
Let me. I just want to say that these are two books that we like quite a lot. Here's a new paper that's coming to be submitted to Psychomethods. It's a German team teaming up with Herb Marsh, who's now at Oxford, And it has to do with this thing that Linda talked about, a student-level variable that could be modeled on both within and between. It's an idea where Mplus actually creates the between-level part as a latent variable. You don't have to create a y bar sub j variable, an observed between-level variable, but it's actually automatically created in Mplus. And this article contrasts those two approaches, the standard two-level approach of using y bar j as a predictor or an outcome. Maybe I should say x bar j is a better example, x bar j as a predictor, versus a latent x bar j. So that in an applied paper, if you're interested, we'd be happy to send it to you, but it's coming. Probably going to be published in Psych Methods. Yes?
I have a question about something that Linda mentioned on slide 26.
26?
Yeah, you said that it's 30 to 50 plus is recommended. And I was wondering, what about a situation where, say, you have a much less ambitious project, maybe, not 14,000 people.
Right.
But you haven't had a sample from a number of different schools, maybe 6 or so, and you just want to account for the fact that you have responsive structure, but not necessarily model effects.
Exactly.
So is that allowed?
Well, I think that you would create dummy variables, right? So if you, let's say you have 6 schools, you would create 5 dummy variables to represent those schools, and then include those as covariates in your model. That's the most you can do, I think, in that situation.
Yeah, so it's basically taking a fixed effect approach instead of a random effect. So when you have only 6 schools, you can't really argue that you're sampling from a big pool of schools and draw inferences. But there may still be school differences if you pick those up by a dummy variable.
I actually almost said that on that slide. And I thought, oh, let's not muddy the waters.
This is an interesting and difficult topic. I don't think the statisticians have been really giving full answers to this question yet. So often do we have, say, 10 or 15 schools in our, say, intervention studies. And the question is, what do you do? You have to treat it as a fixed effect in a dummy variable approach. Well, there is an alternative that may be useful, and that is to take a Bayesian approach, where you can use, if you have pilot data information, use some prior information to be able to estimate school-level variances nevertheless, even for such small samples. But how well that works, I don't think we know enough. There's also a possibility of doing so-called bootstrapping to get standard errors that are correct in those cases with very small number of schools. But that's an area where we'll probably see more method development in the next couple of years.
Yeah, can the value-added model consider kind of multi-level regression?
I'll let Bengt answer that.
So you're asking about the value-added model? Can that be used in a multi-level setting? Yeah, I don't see why not.
It's using the random effect as well.
Right, it's a regression model, so yes, certainly.
Yes. Yes.
With the clustering, can you do interaction analysis?
So like a latent variable interaction or some other interaction
Like
included?
moderation analysis?
Yes.
But don't you have to use random?
You can include the X with command, right, in 2-level? Right, so if you have observed variables, you would just create an interaction variable. But you mean a latent variable interaction like we talked about yesterday with X with? Yes, X with can be used with type equals 2-level. So you would just you would need type equals random 2-level like I showed with this. And then you would have to have latent variables in the model, or one latent and one observed. And then you would just use the X with command to define that interaction. And then you could put that interaction. And the reason you can do that is because that's a latent variable, and we allow latent variables as covariates in these types of models. And I think that's unusual, right?
Yeah.
Right. So that's not always done, but we do that in Mplus.
Okay, when you look at the results that you get on number
34? Oh, wait.
33?
32, 33.
32.
Those are both safety. Is there any any figure on those 2 pages that gives you any indication of the power of the output?
So the power to detect that those coefficients are different than 0?
Powerful, right.
Right. Not here, but you could do a Monte Carlo simulation study based on this, on your results. We actually have an option in Mplus. If you don't know your population values, you can save your results and use your results as population values in a simulation study. And then you can use your sample size that you have, and then you can see whether you have the power to detect that a particular parameter is different from 0 with your sample size.
You can't say, there's nothing to say that this analysis.
No,
I
don't know of any way of looking at power just from analysis results. I think you have to do some sort of a power study to determine that. I mean, if you have a tiny sample, you could say, maybe I don't have enough power. But, or a really large sample, oh, I must have the power to detect anything, but anything in between there, I don't think.
Well, when you get standardized results, you get your standard, the beta coefficient. You can figure out a power from that, but you don't get standardized.
Well, you can get, no, you can't get standardized with random.
Right.
But maybe you have something more to say.
No, there are no automatic power formulas. You would have to do a separate power analysis.
Okay.
Thank you.
So we cannot get standardized solution from the multi-level SEM?
It's for the same reason that you can't get the chi-square. You have more than one covariance matrix, so what variance would you standardize with?
You have this formula on slide 36, formula 103. The variance of y changes as a function of the x value. So which variance would you use to standardize?
We've been talking about this. Maybe you would use the average over the clusters, but I don't think there's been any statistical proof that that would have any meaning. But that's certainly one of the things that we're always trying to add new things and trying to research new things. So it's something we talk about frequently.
Now you could standardize yourself probably with respect to the x variables. You can do that by hand. But the full standardization with respect to y as well is ambiguous here.
Somebody over there, because I've been confused. Sure.
39.
39?
29.
29?
Yeah, 29. No, that's slide design, not finish. Yeah, that's this page. Within the 2 regression equation, that's the 2 simple regression or 1 multiple regression. Like if you use S1, S2.
So it's one regression.
Right. It's one single regression, but we just talked about the 2 random slopes separately. But since you have the same variable here, M92, it's one and the same regression equation. So you're talking about the partial regression coefficients in line with the picture.
Can that simplify like S1, S2 bar and the M?
Or you want to have a simplification saying S1, S2?
Yeah.
M92 on female student SES?
Right.
You'll have to talk to Twee about that, and I don't think you'd want to. Okay.
Simple technical question about this slide. You talked about the situation where you change this to a fixed effect. When do you take out random? Like when you have a mixed effect in the analysis command?
So what's the...
Like in this case, you have all random text. But you talked about the scenario when you change it actually to fixed effects.
Right.
And when do I leave in or take out the random command? This is all fixed or?
Random is necessary whenever you have any random slope.
Just one?
Yes.
Okay, yeah.
Except in a growth model. So if you had, if you took away these, you could take away random. But if you only took away one, you'd have to leave random.
Okay, yeah. And I have a second question. What's your advice on model comparison? Because you also provide the information indices and stuff like that.
AIC and BIC.
Yeah.
No advice. You're on your own.
You can do it.
I typically only use AIC and BIC when I use fixture modeling, finite fixture modeling with latent passes, decide a number of passes. I personally don't use it otherwise, but that doesn't mean it's not useful. So
I think we would
like to give.
we would typically look at nested models only in this situation, right?
Yeah. So what we look at compare models is you look at nested models and look at log likelihood differences types of.
-2 types of difference.
What if you have two clusters? If I have siblings in schools?
Oh, we're going to be talking about a nice approach for that later. Is that okay? We ready?
That's under the heading multivariate, the multivariate approach to multi-level data.
And actually, that's if you have few enough schools, it's something you might consider.
It's simple technical question. I think go to slide 31.
31.
The Mplus is the ITC value, but I was wondering if you provide standard error for ITC value.
Standard error?
Standard error for the ICC. One could provide that, but that's not part of the output. But in principle, you could use that actually by an Mplus feature called model constraints. You can define a parameter yourself, between divided by
Plus.
between divided by the total, and that's then a new parameter which will be given a standard error through the delta method automatically. So you can, by labeling certain parameters in the model and using model constraint, you can get that.
Giving this side a chance. Yes.
Slides 35 and 36.
You do 35 and I'll do 36.
In the case where you have that crossover interaction, supposed to do the analysis and the slope is not random, and but you have the interaction, you hypothesized it. Can you set the residual of the slope to 0 and estimate the interaction? And if you can do that, how would you estimate the standard error? So how does Mplus estimate the standard error for that crossover interaction term with the residual set at 0?
If you put 35 on, I'll put on 34.
Okay.
So just to recap that, so when you use the typical random and have a random slope, you can actually, another more complicated way of saying that you have a fixed slope is to say that first it's random and then fix its variance to 0. That will become a fixed slope then. And, but you can, yeah, so that's one way of doing it. Then you will have the fixed effect part. Then you will, beta 1 will be this much and not that. I think in Raudenbusch and Bragg's book they call that slopes that are varying but not random slopes, something like that. And then you get the interaction effect nevertheless. And you still stay in the maximum likelihood estimation framework and get the standard errors through the usual information matrix.
But what's the end? Like, would it be 1,000 the individual level sample size, or would it be the group sample size for estimating the standard error?
Well, essentially then it will be the individual level, I would say. You would not be bothered by any between level variation. But it's the same formula, drawing in the information matrix to get the standard error.
And it's not going to create a standard error that's too optimistic?
No. No. It will be the right standard error. You pick them?
Okay. In the middle, right here? Yes.
In the S30.
Sort of.
Side 30?
So what you suggest for the minimal sample size within a class? So you see here just one observation within the school, but some statistical
I'm sorry, I can't hear. Can you hear me?
Yeah, so I think the question is about, should we worry that some clusters have only one member?
Yeah.
No.
That means that that cluster cannot, these clusters, these 1, 2, 3, 4, 5, 6, 7 clusters, cannot inform you about within cluster variation because they have no within cluster variation. But they do inform you about within cluster mean related parameters. So they're useful to retain. You will keep information from these as well. But in terms of within cluster variation, you have to look to the other schools to give you information.
How about back here?
I also have siblings within schools, but not only that, in the longitudinal multi-level analysis, the siblings within schools also change classes, move to different schools. Would you talk about that too?
So you're saying when people move out of one cluster into another cluster, for example, I don't think we can handle that right now.
Yeah,
Is that
this is,
correct?
for those of you who were here yesterday, we talked about modeling frameworks, and I'm going to get back to that when we talk about longitudinal multi-level data later on this afternoon. And there is a part of the current Mplus multi-level modeling box facilities which does not cover what some other programs can do, such as MLWin. And that's applicable to your situation, where students change schools or change classrooms, change cluster membership across time. And that's sometimes dealt with using cross-random effects, which Mplus does not incorporate yet.
Which one does?
I'm sorry, what?
Which software does?
MLWin and I think HLM also do that. Now, the question is how well that can be done. That's another question. And the other question, furthermore, this question about which cluster membership is more important. Very often it's the initial cluster membership that is more important for development in terms of modeling it, apart from correcting the standard errors. But yeah, the multi-level softwares that have been out there for a couple of decades are in some specialized cases ahead of Mplus.
I
Yes.
have samples. I wonder whether they're from the same population.
I'm sorry, can you speak up a little more?
I have 2 samples. I wonder whether they're from the same population. So what is your recommendation of trying to do some testing?
2 samples from...
So the question, just for those of you who didn't hear it, 2 samples, and the question is, can they be thought of being from the same population? That sounds like multiple group multi-level modeling, like we talked about yesterday. You were here yesterday, right? Yeah, so for instance, gender, you have 2 groups. You're trying to test if the parameters are the same. In your case, you have 2 samples. You're testing whether or not they have the same parameter value, come from the same population. That would lead to multiple group analysis in the multi-level setting. And that's quite feasible too.
And we'll talk about that this afternoon, I think.
Yeah. Steph.
Yes. I have 2 questions. First of all, let's say, for example, you want to model individuals within families. How many people within a family do you need to reliably estimate? And secondly, how would I estimate a random effects regression where my level 1 coefficients are random, but there are no level 2 predictors. They intercept.
Right. So the first question is something we'll talk about in terms of the multivariate approach to multi-level modeling. The multivariate approach is a little different than what we're talking about here, in the sense that what we're talking about here, all of these students within schools are considered statistically equivalent. All the students within the school are considered statistically equivalent. When you talk about family members, you probably don't want to take that path. You probably want to take the multivariate approach instead, where you treat an older sibling as having certain qualities than a younger one, and a female different than a male. So we'll talk about that more than this afternoon. Then the other part, you can certainly have a random effect like a random intercept without having any school level or between level covariate trying to predict the variation in it. You just estimate its variance. And having done so, you've done what you should do to correctly get this, to get the correct standard errors. So you don't have to come up with level 2 predictors. Yes, gentleman there over in the back, yeah. You, who look back, yeah.
Two questions. One is, if you just want to estimate school-specific or cluster-specific intercepts, random intercepts, and no random slopes, do you still need the random statement?
No. You only need a type equals random statement if you have random slopes.
Secondly, if one of the tricky things about this kind of analysis is that as the relationship between y and your model gets non-Gaussian, heteroscedasticity can be an issue, at least for well, the fixed and the random part of the model. And so there are torturous discussions in the literature about examining model residuals and diagnostics. Have you given any thought to model diagnostics and residual analysis in Mplus?
Well, yes, we have, and it's an area that we want to develop in further in the future. At this point, you can estimate the cluster-specific effects using this so-called factor score option, which is then giving empirical base estimate. And then by subtracting that from the observed variables, you can get the residuals, compute them in that way, and examine them, but they have to be examined outside of Mplus. And what we want to do in the future is to be able to offer that examination within Mplus.
Couldn't you examine them in the plot command?
You can.
To some extent?
But you don't get the residuals as part of...
No, but what I mean is in a two-step analysis.
Yeah, in a two-step analysis.
Right.
But heteroscedasticity, actually, if that's the main concern, it can actually be modeled directly, as it can in single-level regression. You can have random slopes also in single-level regression, as econometricians have worried about. And similarly, you could do that in two-level regression, where you have random effects then on the level 2. So, but just to go back to the single-level regression, if you have a random slope there, that says that you have heteroscedasticity. So we have an example of that in the user's guide, referring to the econometric literature, to show the model and test the degree of heteroscedasticity. But I would say, generally speaking, that's an area where we want to do better in the future.
Any other questions?
Over here, I think I've seen
Okay.
this gentleman raise his hand.
Two questions. First, how does Mplus handle missing data on the covariance side? I know that you can have missing data on the outcome side, the within level. Or what if you have missing data at the cluster level?
Missing data on the cluster?
Missing on the cluster predictor.
So like the W that Linda was talking about. Right. Well, generally...
Well, generally speaking, if you have missing data on your covariance, that case is eliminated from the analysis because missing data theory doesn't actually cover covariance because the model is estimated conditioned on them. You can bring the covariance into the model, and then distributional assumptions will be made about them, just as are made about dependent variables, and then they won't be eliminated from the analysis. I don't know how I feel about that. You know, we say that, but you might want to comment further on that.
Yeah, if you bring the W variable into the model, in which case you can deal with this missingness, then you're also making a further assumption beyond that you have in the model. In this case, typically then that W is normally distributed, which it may not be. But that's the same assumption that you would make if you take the alternative approach of using multiple imputations, an Bayesian approach. So you can certainly do multiple imputation procedure to fill in missing data for covariate as a first step. But there also you would make distributional assumptions. But actually, we made Mplus be able to take multiple imputed data from other programs and do the correct standard error calculations from those multiple imputed data sets analyzed multiply.
But in a within between model, you could, what you just suggested about using multiple imputation, you could only have missing at the between level, right? Because if you had also missing at the within, that would be sort of doubly there'd be double computation.
That's right. That's right. The standard error formulas would be more complex then. Yeah, and that's not covered yet.
The second question I had is, at the within level, can you calculate an indirect effect?
Yes, our model Indirect can be used with two-level analysis.
Right. So the formulas are extended to that case for model Indirect. Model Indirect. Is that a command?
Model Indirect's a command, yes.
Okay, thank you. Lady over there on the left, yeah.
Yes, on slide 35, you talk about how level 1 effect can vary between clusters in the cross-level interaction. I'm curious about whether or not you can look at how a level 2 effect varies by a level 1 variable such as gender. And I know you mentioned the multiple group approach, but in the multiple group approach, in my case, I have different groups within my cluster, like different genders within each cluster, like classroom. So I'm not able to do that. So I'm just wondering if there's a solution to that in your program.
So are you saying, could this be gender?
Right. It's exactly right. The moderating variable is a level 1 variable, not a level 2.
Yeah. See, I think I know what you're asking. You're asking about group differences on the within level,
right?
Not on the between level, and that's a good question because that is not covered here. It won't be covered by us in the afternoon. But I'll give you a hint. It's a paper I've wanted to write for some time. I haven't had the time, but maybe if you have the data, we can collaborate. The way to do it in Mplus currently is the mixture modeling, finite mixture modeling, where you can see the grouping level, the within level group variable is treated as a latent class that is known. The known class combined with multi-level would do what you want to do.
So is it wrong to treat, because these are both observed variables, so I created an interaction term previously as a variable in the data set and used that on the within level, but is that something that's just not correct?
Yeah, that's not totally correct. I don't know how close it is then.
Great.
Sorry.
Great.